Okay, so now this is the final session of Gonzalo course, quantum thermodynamics.
Okay, so welcome back. This is the last session of this mini tutorial course on quantum thermodynamics. So yesterday in the first part, we just have seen some background about quantum measurements and about open quantum system, more in general. This morning, we have seen a little bit about quantum thermal machines, heat engines and refrigerators, some like basic models for that engines. And in this last part, I will touch on fluctuation theorems for quantum systems. So all what we have seen until now has been like average quantities mainly. So in the heat engines and so on of this morning, we were talking about heat fluxes and output work, input work, but we were referring to averages, okay, everywhere. Except in the last part that I told you something about the variance of the output power, which has to do with the fluctuation, but I didn't tell you how to calculate it. So after this, you will have a more clear idea, hopefully, about this kind of things. So the point is that, well, let me just put the title here. This is about fluctuation theorems, quantum fluctuations. So the main idea is that as long as we are interested in small systems, the fluctuations become more important, right? So at some point they cannot be neglected, no, from the point of view of the energetics or the entropic evolution of a system. So introducing fluctuations inside the thermodynamic framework has been first done in stochastic thermodynamics, okay? Now, and this has been done with a great success. So it has been applied afterwards to biology, to chemistry, or to physics in general. And in that context, there has been some particularly useful relations that has been named fluctuation theorems. And essentially, they are a set of identities, so usually equalities, that somehow extend the traditional second law, so the increase of entropy in the universe, to the fluctuating level. So in particular, what they do is that they put constraints on the statistics of the thermodynamic quantities. So for example, on the work, on the heat, or on the entropy production in some process. And the good thing about them is that they are very general, they are universal, and they can be applied for situations that are arbitrarily far from equilibrium in general. So this is what makes those identities so powerful. So the most famous fluctuation theorems comprise the Jarzynski equality, which is also called the work fluctuation theorem. Was derived in 1997. Also related to work, it's the Krug's. There is the Krug's fluctuation theorem, which is related to the Jarzynski equality. It's more powerful than the Jarzynski equality. It's related to it. I think it was derived a year in 98 or so, or 99, I don't remember. Then we are going to see another kind of fluctuation theorem, which are called exchange fluctuation theorems. which in this case involve the heat exchange between two or more systems. So they constrain the statistics of the heat exchanges. And finally, we are going to look to fluctuation theorems for entropy production. Which are somehow the most general ones, no? Because entropy production can be related to work, to heat, etc., depending on the situation. So, okay, so we are going to see how to obtain this kind of fluctuation theorems in the case of quantum systems, okay? And, okay, so let's start with, well, let me Okay, so I will start first with fluctuation theorems for isolated quantum systems. And for this part, I will be, so it's based on this review. It's a review by Michele Campisi, Peter Hangi, and Peter Turner. It's a review of modern physics. Okay, so the first thing to notice is that in order to define fluctuations in a quantum setup, we need to implement some measurements, because we have seen the first day that even if we have a pure state, the specific values of some observables may not be well defined. So what the first thing that we need to introduce is what is called this two-point measurement scheme. What this means is that essentially, if we want to assess the fluctuation in some process, we will introduce some ideal measurement at the beginning and at the end of the process over the system of interest that we want to assess. So in the simplest case, the measurements are taken to be energy measurements, so measurements of the Hamiltonian, right? So we can imagine a process in which we start with some initial state rho 0, with the initial Hamiltonian H0, with some spectral decomposition like this one, right? So then we first measure the system using these projectors of the energy at the beginning of the process. So we will get some outcome n and some eigenvalue as a result of the measurement, as we have seen yesterday, right? Then we can change the Hamiltonian arbitrarily. So we may have some Hamiltonian may depend on some parameter lambda, the control parameter, such that it follows some protocol defined just as the sequence of values that lambda takes from time t0 to some final time tau, right? So if the system is isolated, then this process can be just described by a unitary evolution that depends, of course, on this protocol that you are implementing, right? So of course this u is, as we have written the other day, is just this exponential of minus I, the integral between 0 and 2 of the Hamiltonian, right? So that we start with the system, we measure, we implement some external driving, so the system can change and can go out of equilibrium, whatever. And then at the end, we will introduce a second projective measurement, which will be so we will measure the energy at the end, okay? So at the end of the process, so at time tau, we have the Hamiltonian. We can also write it as in a spectral decomposition. So we will have some new eigenvalues Em prime and another projectors P prime. Okay, so doing this, we are now able to talk about the work fluctuations. So what will be the work fluctuations here, how are defined? We just define it as the final outcome of the energy minus the initial one. Okay. So notice that even if this unitary is deterministic, since we have these measurements at the beginning and at the end, this is a random variable in general, right? Sometimes you will get some final m, so m equal to 1 or to 2, depending on the different levels. So this is a stochastic. Okay, so what is the probability of a specific trajectory? And what I mean with trajectory at this moment is just that I have some initial outcome n and some final outcome m. Okay, so for now my trajectory is just the outcomes initial and final of the measurements. I put trajectory. So the probability, so and this trajectory is essentially that I start in some initial state, which is let's say Am, it will be like the eigen state of the energy at the beginning, and then it will at time tau I will have eigen state Am prime. So the probability for this to happen, it can be calculated just using the Born rule, no? So it's that will be the initial probability that I have to measure n, and then this bracket, which is essentially the probability that given that I obtain n at the beginning, I evolve, and then I obtain m at the end, right? So here, Pn is just the initial probability, so the probability that that I get outcome n in the initial state, and yeah, and just that. So with this, we can also define a work probability distribution for this process. So the work probability distribution can be defined just as P of W. It will be just like a sum over all the probabilities to have the different trajectories and some Dirac delta that points just to these possible values of the work. So what that means is that our probability distribution will be discrete. So it will be a collection of peaks at the different possible values for the work, depending on the initial and final outcome, right? This is what this means. No? You have this direct delta with the integral, just so this will look like this is W, P of W will be something like this, no? We'll have some point here, some like just discrete points, right? Corresponding to each of the values, each of the possible values of the final minus initial energies. Okay, another concept that is also used a lot is the characteristic function of work. And this is just the Fourier transform of the work probability distribution. So this will be just this guy. Okay. So in our case, what we will obtain is that G of U will be, well, but this is not important. Okay, this is just a definition, okay? So now we can state the Jarzynski equality, okay? The Jarzynski equality is, it can be described in this kind of framework. So the idea is that the idea is that we have an initial state which is in equilibrium, so it requires that my initial state rho 0 is in thermal equilibrium at some temperature, inverse temperature beta. So the idea is that I start in equilibrium, so that we can just imagine like, I don't know, something like a potential, and that will be like the distribution. This is pretty classical, but this is just to give you an idea, no? Then you will implement some protocol lambda, so you can modify this potential, so finish, I don't know, in some, let's say, double well or whatever. And of course, in doing this, the distribution will change, will be arbitrary out of equilibrium. I don't know, maybe like this, I don't know, whatever. Can be. And then we will compare with what happens if we just let relax this to a new equilibrium state for the final potential, right? So we will be comparing to some equilibrium distribution at the end, no? So that will be just the state at time tau, and then we will also use like some thermal state that let's call, well, we will compare also with this state, no? Same temperature but the final Hamiltonian. So So what the Jarzynski equality tells us is this thing, is that the average over many realizations of that process of e to the minus beta w, it will be equal to e to the minus beta delta f, where delta f is the change in free energies from the initial to the free energy of this guy. Okay, so this initial state will have some free energy F0. This state, thermal state, will have some free energy F tau. So what it tells us is that the average of the work in this process over many realizations just equals this guy. So it relates a property which is completely out of equilibrium, which is the work in this stage before thermalization, with the change in free energy of two thermal states. Okay, indeed, has been used in the classical case to infer changes in free energy in systems that are difficult to calculate, right? Just by running a protocol many times and making these averages. So, okay, so let me just give you the proof of this. For that, I will need to erase something. Okay, for the proof, I will calculate the characteristic function, which will be something like this, which is if I introduce the probability distribution of work, I will get something like the sum over n and m of these trays. So essentially I will have here, well, I will have this prefactor e to the I u m prime minus n. That was the prefactor here. And then I will have a trace over the final projectors, initial evolution, initial projector, for this thing, no? Sorry. No, sorry. Yeah, and the initial state. Sorry. Right. So that will be the. So that will be this P0, right? That we introduced before. The probability that my system is initially has energy En. No? Because now I am assuming that I start in equilibrium. So then what I will do is to use the fact that those are projectors on the energy, in the Hamiltonians. So that I will reorder this. So this is just equal to this, right? Here I just introduce these scalar quantities here inside. And then I use, what I will use is the following, right? It's the fact that if I multiply like e to the I u h tau by pm prime, then I get e to the I u m prime vm prime, because this is one of the projectors of the Hamiltonian, right? And the same thing for the other. So with the initial Hamiltonian is pretty the same, because I have the projectors. So if I put the projectors of H0, then I will get this thing. No? So that if I do that here inside, I just get the following. Yeah, sorry. This thing by n and then. Okay, and then yeah, I forgot set 0. Okay, so now if I look inside my equation, I see that the only things that depend in n or m are the projectors, and I have a sum here. So I can just sum these projectors that provides the composition of the identity, right? So the sum over n of these guys will be the identity. The sum over m of these guys will be the identity again. So essentially, what I get is this thing, no? Right? And hence, if I calculate, if I evaluate the characteristic function on I beta, that is by definition this average, right? This is just because of the definition of the characteristic function. And if I introduce u equal to I beta, this will goes to 0, this thing in the inside this exponent, so that this exponential will disappear. Then I will have, well, so I will have something like this. Trace, so this will disappear. Then u times u dagger will be the identity. And I will remain only with this first term, e to the minus beta h tau divided by z0, right? But this is nothing but the ratio of z tau divided z0, which is just e to the minus beta delta f. Okay, so we reach the proof. Okay, this is just the last thing is just we use that beta f at any, so at the time tau or 0 is just minus the log of z at that time. Okay, we use that property. Okay, so that is the proof. Now let's see some of the consequences of Jarzynski equality. So, okay.
Sorry,
Yes.
what is the meaning of u at the characteristic function?
What is the meaning of u?
If what is the meaning? What is the meaning of u at g of u, the parameter u?
It's just the variable that of the Fourier transform of this distribution. It's not changing from, let's say, usually it is used for changing for time domain to frequency domain, right? Here is something similar. We just change from work, this variable work, to a variable that will be like the complementary or something like that, no? But okay, so yeah, so let's go to some consequences. And perhaps I can do it here. Okay, so the first consequence is that from the Jarzynski equality, let me just have it here. From this, we can recover the second law of the average level. Okay, that will be, so standard second law. And for that, what we are going to is what is called Jensen's inequality. So can you see this one, or perhaps I change? Sorry. I think this one was good. Thank you. Yeah, I can. So the Jensen's inequality is very general. It just says that if we have a convex function, f, if we evaluate the average of a quantity, this will be always less or equal than the average of the f of that quantity. So that essentially means that if our function is convex, we will have, let's say, I don't know, x1 and x2 here, right? If I evaluate the average of these two guys, will be always greater than this point, no? So the function on the average is always less or equal than the average of the functions. If I have a, and this is true for any function. Now I will apply this to exponential. So if I do that, it is like, well, I have Yersinski equality, that is this thing here, but I now can say that this is greater or equal always that e to the minus beta, the average of work. So this, from this part, that beta is less or equal than beta, the average work. And this essentially is that the average work should be always greater or equal than the. So essentially we recover what we know from classical systems, right? That the average work, in this case is the average, should be always greater than the change in free energy, which will be the work that we could recover from the final state, no? And of course, yeah, this is for any protocol lambda. So another consequence is the following. Sorry?
Before you erase this, end of erasing, finish erasing this, can I ask you a question?
Yes, sir.
So, as a requirement, you ask is, can we talk about free energy when you don't, in cases when you don't start from thermal equilibrium state?
Free energy is an static concept. So you can talk about free energy of a equilibrium state, but you can also talk about free energy like non-equilibrium, just like as the energy minus kB T, the entropy. And you can use here, for example, the Bernoulli entropy. Okay? But here I was referring about changes in frequency of equilibrium states, so the traditional ones, like M-hole free energy. But this concept also exists and can be used in some situations as well. No, the Jasinski equality relates non-equilibrium work with equilibrium free energy. But there are other fluctuation theorems, such as, for example, for entropy production. Particular situations give you something related to the non-equilibrium free energy. Okay, a second. Is positive, but we can have instances in which we have less free energy change. And so now the fluctuation theorem tells us things about what is the probability of that cases, right? So the Jasinski equality directly implies the following thing, which is that the probability that the W minus delta F in a particular instance of the experiment is less or equal than some, let's say, a constant psi with this positive is less or equal than e to the minus this quantity. Okay, so what this guarantees essentially is that if I have my probability distribution for work, that as I said before will be something with some delta points, and if I have, for example, imagine that here is delta F, so I am guaranteed that this tail of the distribution decays exponentially with W. Okay, this is exponential. So the distribution is less than exponential, no? And so this can be proved also from the Jasinski equality. So the idea is that this guy here can be written in this way. So that's the integral minus infinite delta F minus this quantity. Of the work probability distribution. So this is this left tail to the left of delta F. And this, so this should be less or equal than the same thing, but multiplying it by this. Because we said that in this tail, this will be greater or equal than 0. So then, if we go with this out, we will get it to the beta delta F minus this parameter out. And this integral here, in which we will have just the work probability distribution and this prefactor. And now what we can do is that say that we can extend this limit up to plus infinity and say that this will be greater or equal because this is a probability distribution or this is positive inside. So this is just this thing. And now, so if we go with this to infinity, we just get here this factor, right? So that if I now use the Jarzynski equality, it tells me that this is just e to the minus beta delta f. So this cancels with this one, and this just give my minus beta and the parameter. Okay. So that will be the proof of this claim. Thank you. Okay, so now we are going to see a related theorem, which is called the Crookes fluctuation theorem, also called sometimes detailed fluctuation theorem. Okay, I will have to erase. Thank you. Let's see here. Okay, and for this, so what this theorem does is to compare the probability distribution of this process with the probability distribution of a process which is like this but time reversed. Okay, so the first thing that we need in order to state this theorem is to define what is the time. And the time reverse process essentially is reverse order. But for the case of quantum mechanics, we will need also to introduce an operator which is called reversal operator. So it's an operator which is anti-unitary. That means that it fulfills the unitary equation. But if I act with this operator over the imaginary unit, it changes the sign of the imaginary unit. And why this is needed? This is used to, so if you apply this operator to, let's say, some state or some some observable, it changes the variables that are odd under time reversal. For example, momentum. No? If I have a state with momentum, I don't know, pointing in that direction, I apply this operator, and then the momentum will change as if I was like going backwards all time, right? So for example, position will not change, but momentum will have a minus sign. Same happens, for example, for magnetic field. We have a magnetic field in some direction. If I apply this time reversal operator, it will change. But in many cases, we use Hamiltonians that does not depend on this kind of odd parameters under time reversal, and in that case, this makes nothing, essentially. So the idea is that now, what we are going to do is that, well, we are going to start with some initial state that I will specify later, and then do the opposite thing. No? Now, I will apply operators by m prime, but I will use also this time reversal operator applied to those operators, those projectors. It's just useful in the case in which I have magnetic fields or things like that. Otherwise, they they don't do anything, okay? Then I will have the unitary evolution corresponding to the time reverse control parameter. So this essentially takes just the opposite sequence of values. And finally, I will have again another projector corresponding to H0, but using also the time reversal operator. This is just because now what we want to measure is theta H tau, theta dagger, and here theta H0, theta dagger, right? So that if it depends on a magnetic field, the magnetic field changes, for example. Okay, so introducing this process, now I can compare trajectories in this process with trajectories in the original one. So for example, I can define this trajectory that is the opposite of the one I introduced before, which is just obtaining the outcome M and then the outcome N, right? So, and I can define also like the work in this time reverse process, which will be just En minus Em prime. So it will be just minus the work in the forward process, right? So I can define everything for the time reverse process as I did for the forward process. It's just that I use a different protocol at the end. So I can define also the characteristic function of the time reverse process, and so on and so forth. Let me just write down the work probability. Like before, but now I have this. Oh, sorry, I did not introduce the probability. So yeah, so let's introduce the probability. Well, let me write this. Right, it will be very similar to the opposite case. With this guy, the probability distribution, so the probability that I get this trajectory in the time reverse process. So that will be the initial probability that I get outcome M, and then this thing here. Right? This PM tilde, just the probability that I get outcome M in the initial state of the time reverse process. Those are just definitions, right? Now, now we can state what is the Crookes fluctuation theorem, which is this thing. So essentially, what it means is that the work probability distribution in the forward process of having some outcome W divided by the probability in the time reverse process of having minus W is equal to e to the beta W minus delta. Okay, that is the statement. And so that tells us essentially is that it is much more unlikely to recover work than to perform that work, right? If I put this here to the right and this exponential I put the other side, I will see that the probability that I recover some work that I put in the forward process decreases exponentially. Okay. So this is slightly more powerful than the Jarzynski equality, and indeed, Jarzynski equality can be derived from here. But let me first prove this theorem. The key thing is so the key property is the microreversibility of the dynamics. And what means that? So microreversibility, this is a general property of quantum evolution, or also Hamiltonian evolution in classical systems, that tell us that this unitary describing the time reverse protocol, it will be equal just to the unitary of the forward protocol dagger. Okay? This is called microreversibility for non-autonomous systems. So it happens that if we have this, now we can look at this expression, right? So let's calculate the probability in the forward process of a trajectory divided by the probability in the time reverse process of the same trajectory backward in time. So we will have Pn times this thing, and in the denominator we will have this Pm tilde and the opposite thing. No? But if I use this equation and I introduce it here, what I get is just U lambda dagger, and I can just flip all this, which will be exactly equal than the numerator here, right? So these two are equal, so this is equal to 1. So it means that the probabilities, the ratio of the probabilities, only depend on the initial probabilities to be in outcome n or m. So that if I choose like Pn equal to E minus beta En over Z0, and if I choose the initial state of the time state with the final Hamiltonian, right? So so what we call Pm tilde e to the minus beta Em prime over tau, then this will be just something proportional to minus beta W minus delta F, right? So now I can use this to prove this statement, and this also easy. The idea is that this is the quantity of work okay. So what I'm going to do is to change this by this factor times this probability, right? So this is the same integral, same sum over n and m, and now I will have p n m p tilde and the factor e to the minus beta w and m minus delta f, delta of w minus W and M, right? But now, since all these cases, well, delta F does not depend, nothing inside the integral, and this W and M will be always W because of the direct delta. So this, I can go out with this factor. And I just remain with this thing, right? Right? But I said before, W in the time reverse process is just minus W of the forward one. So this is plus W tilde and M. So that all this is just the probability of the time reverse work distribution of minus W. And this is the proof. Okay. So there is another alternative way to prove the Crookes fluctuation theorem, also using a relation between the characteristic functions of the forward process and the one of the time reverse. So I will not talk too much about that. But now I would like to show you a couple of slides regarding this part. So if it will be possible to... So is there any question in the meanwhile about these things? Yeah?
Does property of reversibility is a theorem or it's a hypothesis?
No, it's a theory. It's I will show you a picture that will combine two. No. It's a general property of unitary evolution. I mean, it's also true in classical mechanics for Hamiltonian evolution. Here is it. So, yeah, what the micro-reversibility says essentially is that, is there any pointer, or even this one is okay. No, it's okay. So if you start in some state and you evolve according to the protocol, this protocol, so you will in general go to whatever other state, rho t, and at the end rho tau. If I apply here the time reversal operator, I will go here, essentially. So I just put here, like if this was like momentum, so momentum will change sign. And then if I apply the time reverse protocol exactly, so I will go back and I will reach this state. So if I apply again the time reversal operator, I will go up to the beginning. And this is just because the unitary evolution here is completely deterministic and you don't lose any information. It's completely everywhere. And this is what reversibility. And turn back to use. So, yeah. So this is essentially the statement of micro-reversibility. And this works for every, whatever the protocol you put in these equations. Okay. I wanted to show if this moves on. Oh, yeah, yes, this one. Is that there has been some experiments as well that has been testing the fluctuation, the Crookes fluctuation theorem and the Jarzynski equality in this kind of platform. Those are NMR platforms in liquid state, and so they have these form molecules, and what they do is that they implement like a rapid quench with an RF field. So the idea is that they have, this behaves as a two-level system with some spacing, and then they apply this, change this field so that the spacing goes down, so it's decreased in a very fast manner, and then they compare to the backward process that will be starting in this state with the small energy spacing and go back very quickly to the large one. So what they did here is that they managed to do, so since they have this carbon and the hydrogen and so on, the scheme that they perform is to profit from the interaction between these two, so that then they apply some measurement on one of them and decode the information about the work probability distribution. So what they measure essentially is that the characteristic function of work in the forward and in the backward processes. Okay, so I will not enter into details of how they do that and so on, but essentially it's like they have the system, some auxiliary, and then they perform some interaction between the two, read out the auxiliary, and then get the changes in the energy of the system. So, and those are the reconstruction of the work probability distribution for these cases. So you see that you have 4 peaks because you have 4 possibilities of different works, because they have 2 eigenstates at the beginning and 2 at the end. And essentially, they recover this is logarithmic scale. This is the ratio of probabilities forward and time reverse of work. And this is work. There's logarithmic scale, so they get these straight lines. That means that you have the Crookes fluctuation theorem verified. And they also check what the Jasinski equality. So and here they put the numbers that they get. They measure they put here the logarithm of this factor and beta delta f, and they are pretty similar, right? So they are within the errors. And this is what the theory will predict for the same protocol. Okay, no, this is for later. So we can get out of here now. Okay. Oh, so how much time do I have? Okay. Okay. Thank you. So, okay, let me then go a little bit faster with the exchange fluctuation theorem. So in the exchange fluctuation theorem, as I said before, is about heat exchange between 2 quantum systems. But it is still is like similar to this thing for isolated systems, but it's somehow a step further. The idea is that now we have 2 systems, A and B. We have 2 quantum systems, system A, system B, and the idea is that you have some Hamiltonian for the system A, HA, some Hamiltonian for the system B, HB, and then you switch on some interaction between the 2. So the idea is that you will have some total Hamiltonian. There will be HA plus HB plus H interaction, and H interaction at time 0, and then it can be whatever in the middle, and then at some final time it goes to 0 again. No? So just switch on, do whatever, and switch off. So in general, and the middle is non-zero. So if we start here with a product state, so an uncorrelated state for system A and system B, but each of them is in equilibrium at a different temperature. So this is minus, let's say, beta A, HA we said A, this is e to the minus. And those are completely uncorrelated. Then by means of the interaction Hamiltonian, they can get correlated, they will exchange energy, exchange information, whatever, during this time. Then, we have to implement again this 2-point measurement scheme. So at time, we will make a projection of the Hamiltonians of both of them. So we will get some outcome N1 for the system A, N2 for the system B. Then we will evolve. So they will, yeah. Well, here we then for the measurements En1 and En2 for the two systems. Then we evolve. So we will have again some unitary acting over the initial state. Right, that will be the state at some time t. Well, let's just go to the final time, right? At final time, we will have this state, and then we perform a measurement, no? And again, now everything that we did before, now we do for both systems simultaneously. But the main difference is that here in principle, here we will not drive the system. We just switch on this interaction and then switch off afterwards. But we don't implement any protocol, so we will not input energy on the system in general. We just let the two systems exchange energy between them, but without introducing any external energy. So this means that at the end of the evolution, when we go to zero with this, we will have the same Hamiltonians for the two parts as initially. Okay, now our Hamiltonians of our systems will not change. Okay, so then at time tau, we will have some other energies, M1, M2. So notice that before we have E prime, no? Because that was a different Hamiltonian at the end. Now it's the same, are the same eigenvalues. It's just that here you obtain N1 and here M1, so a different one, but it's the same set. Okay, then if there is energy conservation between these two guys during the evolution, and what this means is that this unitary commutes with HA plus HB, this is zero. That essentially means that the interaction Hamiltonian does not get energy, so it does not get some energy out of the systems. So it not accumulates energy during the evolution. It's just something that allows transfers between this guy and this guy, but does not accumulate energy by itself. So, and this of course, that means a strict energy conservation, but you may also have approximate energy conservation, but this is what happens, for example, in weak coupling situations. Where the coupling is so weak that you are not allowing it effectively to store energy. So if this happens, we will always get that the change in energy in the system A will equal minus the change in energy in system B. And we will call this the Field exchange between these two systems. So that now, if I calculate the probability of a trajectory for those measurements, call it set A, times e to the minus, sorry, it's beta A, and this is beta B. And again, I will have the conditional probability that I have the outcomes M1 at the end. Defined by N1 and right. So again, now it is pretty the same. I wish, because initial and final Hamiltonians are the same. So yes, I just start here, and I will start in equilibrium again. I will switch on the interaction, switch off, and measure the projectors, so that in the time reverse process, the probability will be, so again, starting in equilibrium, but now the trajectory is the opposite, right? Now we have M1 and M2 here. Yes, and then again this trace M1 by N2 unitary, and what will be there. So notice that here I am not using the time reversal operator. It's just for simplicity. I am assuming that it makes nothing on the projectors. Okay, but I can put it, but I mean, once I explain what means, we can forget about it for a little bit. This makes things simpler. Okay, so if I compare these two probabilities, what I will get is the following, right? It's, I will get B. So again, the microreversibility principle will apply because we have a unitary evolution here over the two subsystems. So this guy will be equal to this guy, essentially. Right? So it's because, I mean, I will just put this here and use that I am in the reverse. Yeah, sorry, this is here, this is the reverse. Okay. So essentially what I get at the end of the day is just the part, again, coming from the initial probabilities in the initial state of the forward and in the initial state of the time reverse. So that making the division of these two, I will get that A to the beta 1 em1 minus em1 and e to the beta 2 em2 minus em2, which is just e to the beta 1 delta A e to, sorry, I sometimes put beta 1 and beta 2, it's beta A and beta B. Beta B delta E B. But this is just using this. So this is essential, right, for this theorem. Is e to the beta 1 minus beta 2 times the heat. So as before, with this, we can easily prove that the probability of these two guys are fulfill this. Okay, this is what is called this exchange fluctuation theorem. Okay? It's very similar to the case of the Crookes fluctuation theorem, but it's just for the exchange of heat between these two bodies. Okay, and so this was first derived by there since all chick. Okay, it's like this. can also be extended to multiple bodies and also not only energy exchanges but particle exchanges. Okay, so what's the time? Okay, I have 10 minutes still. So, okay, is there any question about this? Yes?
Do you have an example of a physical system that has a similar behavior of the interaction term of the Hamiltonian? The behavior that you say that at the beginning, at the end, the energy of interaction is zero.
Well, this in principle you make impose.
Okay.
Imagine I put in contact the two systems are separated, for example. Depending on the platform, it can be very different, no? How you do that, or you send something and make them interact. I mean,
Okay.
they can be done in very different ways. Yeah.
Okay. Thank you.
And unitaries that preserve the energy, there are also any, for example, hopping term between the two systems. For example, in like the ones that are like interaction Hamiltonians, like for example, two electromagnetic modes like of this kind of A B dagger plus A dagger B, and will fulfill this equation. Or also, no, if you have qubits like transitions, like from, let's say, if I have a system that goes, let's say, from 0 to 1, and the other goes from 1 to 0, right? So all these kind of interaction Hamiltonians will give a unitary evolution that verifies this property.
Does this scheme includes also to consider considering B like a thermal bath and A like a small system?
Yes, yes, because well, yes, but you are assuming that your system starts in equilibrium at another temperature, right? Than the bath. This is indeed, if you have same temperatures. Sorry, this is beta again, beta A minus beta B. This tells you nothing, right? Because if you're already in equilibrium with the reservoir, let's say, you will not exchange any heat.
Yes, I know the result for the classical.
So indeed, in this paper, they derive this equation for both classical and quantum at the same time. Okay, so then let me just go to the, sorry, yeah.
The interaction Hamiltonian is not occurring anywhere at all during the derivation of the whole theorem. So regardless of whatever is going on with the interaction between the two systems, these holds. That's the point, right?
So, but you need this in order to have here this equation. Otherwise, so I use that here, right?
Mm-hmm.
I use that there, here that this delta AE is, so up to here is completely general. And here I get, just because the change in energy of system A is minus the change in energy of system B. And this you are ensured to have just by imposing this, right?
Yeah, but this doesn't include either the interaction Hamiltonian at all.
Well, but this unitary is
okay. Sure.
Goes with the interaction Hamiltonian.
Thank you.
Okay, so then let me just talking 10 minutes about the last fluctuation theorem, and for what I would like to have the last slide that we had before. I can perhaps start saying something in the meanwhile. So, okay, well, those are fluctuation theorems that are mainly for isolated quantum systems, but of course you can think about, so for the case of the work fluctuation theorems that we have seen, you can think that now your system is not just your small system of interest, but it's the system plus the reservoir, right? And in that case, these theorems will apply nevertheless, right? The only point is that you will need to measure both your system and your bath in order to determine the changes in the energies, right? But now what I wanted to do in this final part is just to talk about another type of fluctuation theorems that are fluctuation theorems for the entropy production, which is like a more general quantity, also can be set in like an information theoretical way. So the idea is that we can imagine a situation which is, but it's slightly more general. So now we have some system and some environment, and now the idea is that the environment will be whatever, and the system will have also whatever initial state. Now you have two initial projectors as before, but this I just initial states, okay? So this is the result of my states and take the projector, so I measure on that basis. So I get some outcome for the system and some outcome nu for the environment. Then I just apply to this global system, right? In general, I am interested in Hamiltonian. Only the system part has a time dependence, while the interaction environmental part are fixed, but it's general. So I will that it's they will share result of applying the unitary evolution over the two subsystems, and then I will apply again two projectors, and in this case I will use arbitrary projectors. So I am not choosing the Hamiltonian or whatever. I say I want to measure that observable in the system and that other observable in the environment. So completely general. So what happens if I do that? What happens is that I get a state which will be like this one here. And this is essentially what we have seen the first day, right? I applied these projectors, and that will be the unconditional state after the measure. So what happens is that this operation here will erase some of the correlations of this state, but not necessarily all the correlations. In general, it will erase only the quantum correlations, right? But it can contain some classical correlations nevertheless. Why? Because if I know what is the outcome M, I could infer something about this system, or the other way around. If I know something about the outcome mu, I will know something else about the system. So the way to somehow to write down this is well, okay, so this rho SE star, it can be also written in this way: sum over M and mu of some distribution, let's call it, I don't know, P or P star, mu times the projectors. Okay, and if I want to look to what happened to either my system or my environment separately, I will need to marginalize this state, right? So I can calculate what will be the state of the system just by tracing out the environment. And this will have some distribution, Pm star, like this, or rho E will be, yes, the trace over the system of the same guy. If you look at the picture again, let's just think about what happens with entropy in a process like that. Okay. So so essentially, we will have some pure state here. So well, let's go first to the average level. So in the average level, as I am measuring just in the eigenbasis of the initial states, this is just like don't disturbing the initial states. So I will just have rho s times rho e and a unitary operation, so the entropy will be preserved. And until here, it will be preserved, right? It's just in the last part in which I will introduce some change in the entropy, no? Because I am measuring, and then the state of the system after measurement, the unconditional state, can only increase the entropy of the system. So what I will have, it's okay, I will. Essentially is that, so I will have the von Neumann entropy of the final state, rho SE asterisk, minus S of rho SE initial, so this one. And this, I will call it the, let's say, the inclusive entropy production. So that I will call it S dot inclusive. here, if I consider this, so notice that I am considering this state, no? So I am considering this state with the correlations that it contains. So here, in general, if I will be in a classical setup, this will be 0, right? Because, I mean, in a classical setup, you can measure without changing the entropy of nothing. So these two guys will be the same, so I will have nothing. In this case, I have something because this measurement is erasing the quantum correlations. But I can also define another entropy production that instead of considering this state, is just consider the state that is uncorrelated. So I can define an entropy production which will be the entropy of rho s asterisk times rho e, so just the marginal ones, right? So, for example, if I imagine a setup in which I cannot have any access to this, so for example, I am forbidden to know what is the come to do something on the other system or something like that, then this will be, it will be the same for me that they have correlations or not. It's like I can forget about that correlations, and then the entropy production will increase. Indeed, so this guy will be always greater or equal than this. Indeed, so what I can write down how this guy will be essentially this one, right? Plus sorry, plus or minus yeah, plus the mutual information in this state minus the mutual information in the final state. Okay, so this is just delta S of system plus delta S of environment, right? While in this one, I will have this part. Okay, and this mutual information is essentially defined as the entropy. So it's essentially the relative entropy between the state, this state, and the corresponding marginal states. Okay. So the idea is that if I forget about the correlations, the entropy production will increase in general, right? So let's just go now to the case of the fluctuations of these quantities. So essentially, what I can do now is to derive fluctuation theorems for these two quantities: this inclusive entropy production and this other non-inclusive entropy production here. Okay. But even more, indeed even more, I can also define another entropy production in which not only I have a change in entropy in the system plus change in entropy of the environment, but if moreover the environment, I assume that this is a thermal reservoir, for example, I will get an extra term here. Okay. Yeah. Yeah, sorry, I think. No, yeah, sorry, let me, yeah, this will be just this thing, sorry. Yeah, thank you. So it is just this minus the mutual information at the end, right? So it's just this field, okay? This is always greater or equal than 0, so that this is always greater or equal than, sorry, lower or equal than this. Okay? So this, you can reach this equation just by the definition of the mutual information, which is also can be defined also as the entropy of one state plus the entropy of the other state minus the entropy of the global, right? So since the entropy of the global is conserved until the measurement, then we will get that, just this thing. Okay, so now we can look at what happens with the fluctuations, so that as before, we will have a trajectory which essentially has 4 outcomes, nm, nu, mu, corresponding to the 4 outcomes of the measurement at the beginning and at the end. And we can again calculate the probability of that trajectory, which will be just the initial probabilities to have the initial outcomes and the trace over all the evolution, right? So now we will compare this with the time reversal process again, right? And for the time reversal process, as before, we did the same, no? With the final projectors, we use the time reversal operator, then we implement the time reverse driving, and we end again by measuring with the initial projectors. So that I have the time reverse trajectory will be something like this: P tilde m, P tilde nu, trace. I will have all these thetas, right? Pn and again, sorry, general sum distribution. In the most general case, I will start in a state that is not necessarily something depending on the outcomes m mu, right? But it could here is that initializing the time reverse process in equilibrium, we will initialize in another state. For example, we can initialize in the final state of the forward process, right? The microreversibility for non-autonomous system, this guy, all the way here, will be exactly equal to this guy. So that I can calculate the log of the probabilities of forward and time reverse trajectories, which will be just the log of these guys, Pn, Q nu, and rho tilde m nu. So now the idea is that depending on how we choose this initial distribution for the time reverse process, so this thing, right? So you see, the only constraint is that it should be something diagonal in this basis, right? Which is the basis in which I measure at the end. That is the only constraint. Otherwise, the distribution in which I start can be general. I can choose different things. So one option is to just finish. So let's now go here. Okay, I will take different options, but well, let me just state the main point. So the main point is that so essentially I can define like some entropy, so fluctuating entropy production that depends on the trajectory, like as the logarithm of the probabilities of having these trajectories in the forward and time reverse process, right? And this will be just equal to the logarithm of Pn q nu divided by this initial state of the time reverse, right? And this I can write down as essentially some delta S for the system that depends on the Nm, some delta S for the environment that depends on nu and mu, and some kind of correlations that depends on the final outcomes. And these guys will be just, so this will be just the minus the log of Pm plus log of Pm, which are the system probabilities at the beginning of the forward process and at the beginning of the time reverse. This for the environment. Sorry. And then this term, which is will be like a mutual information, but in the stochastic version, which will be just the log of this joint distribution nu divided by the marginal ones. Yeah, Pm Q. Yeah, right. So essentially, I get something like a general fluctuation theorem. So this is like a detailed form of the fluctuation theorem. This thing, or a abstract definition, information theoretical definition of entropy production in this process, that essentially depends on the initial state of the time reverse process. So what I can verify now is that if I choose this initial state of the time reverse process to just be rho SE asterisk, so the final one with the correlations and everything, then I will recover this inclusive entropy production, right? So what I can, I don't have time, but in that case, essentially, what you will have is, so you will take out this, so this will just be like the asterisk one, right? And this as well. So you get a fluctuating version of the entropy production with the change in entropy of system, environment, and the correlations. That this is like first option. And if I calculate the average over trajectories of this guy for this choice, I will get this inclusive entropy production. On the other hand, if my initial state is not this state, but just a product state of the marginals of the final states, what I will essentially, so if I choose rho SE to be rho S asterisk times rho E asterisk, so essentially what I am doing is to erase this term because I am choosing this equal to this. So this will disappear here, and I will just recover like a fluctuating version of this entropy production here, just changing entropy of system plus changing entropy of environment. Okay, if I again calculate the average, I will get this change in von Neumann entropy. Even more, I can say, okay, but I don't. So my environment is so big, so it's completely uncontrollable. So in reality, I don't know what is the final state, even the marginal final state of the environment. I don't care about. I just assume that it is equilibrium again, for example. So in that case, I will start the time reverse process with a product state between the final state of the system times the initial state of the environment, not the final one, right? That will be the situation in which I have equilibrium in the reservoir. And in that case, what I get is still another version of the entropy production, which will be just the change in entropy of system plus change in entropy of the environment plus an extra term, which will be a relative entropy between the final state of the environment, rho E asterisk, with respect to the initial state. Okay? And in that case, here, instead of the Q asterisk, I will have just Q, right? It's just the initial distribution of the environment. So those are three different versions of entropy production, and this depends on the information that you decide to keep about the forward process you are running. So if I keep all the information, then I have this expression here, in which the only loss of information comes from the comes from the measurement to the eraser of the quantum correlations. So this is the closer to reversibility that I can get in this kind of configuration. If I forget about these correlations, because are inaccessible to me, then my entropy production will increase, and I will get this expression here, change in entropy in system and plus change in entropy of environment. If the environment is small, I can imagine that perhaps I can do further modifications of the environment afterwards so that it matters the state of the environment after this process. So that will be like meaningful, a meaningful expression. But if I even assume that if I lose the information of the final state of the environment, then I get this final expression here, which is like, of course, this is greater or equal than this S dot, and this is greater or equal than the inclusive one. Okay. The common situation in open quantum systems is this one indeed, because if we have a very big environment in equilibrium, so we assume that the environment so if I now assume that rho E is a thermal state, okay, I can manipulate this expression and show that these two guys together are minus beta the heat exchange with the environment. So that I will be recovering the classical expression for the entropy production. But this is more general, no? It's just based on this notion of informational entropy. So verify the properties that we have been discussing. Notions of entropy production. Oh, it's quite late, sorry.
So at some point you mentioned that here you have both classical and quantum correlations. So classical correlations will come from the fact that the states that you're using are mixed, and quantum come from coherences. Can you distinguish in the
In general, no, in the fluctuations theorem, what you get here is the mutual information after the measurement, which contains only the classical part of the correlations. The idea is that since you are performing this measurement, you are erasing the. So in general, so indeed, so you can manipulate this expression to get the difference of the mutual information before and after the measurement. So this you can do, and that will be the quantum correlations. So in that case, that will mean, so you can rewrite this equation so that you have the change in the drop in the correlations, which will be just quantum part, plus the disturbance that the measurement may do on the marginal states. So this is just, from here you can easily manipulate the expression to get that.
Thank you for the talk. Yeah, so the results are quite general. No? Which these results do these results impose some limits on quantum computation and qubits and these kind of things?
Well, I don't know. I mean, so I mean, if you can write that, so this it's true that this is very general, but I never applied this for the moment to a specific quantum computation protocol. But so they will be verified. So in principle, the fluctuations should verify these theorems as well. No? So I didn't say, but from this, like the tail theorem, you get also the integral theorem, right? Which will be just well, like the Jarzynski equality, but with this exponential instead of the one for the work. So that you will also have the tail decreasing exponentially, and so from this guy, you also get e to the minus delta s, well, s dots equal to 1. And all the consequences that we have seen before apply.
Okay.
So I hope that yes, that you can say also something about.
Yes, because they are always concerned about that, no?
Yeah.
So the stability and so on. Okay, thank you. Are there any other questions? So let's thank Professor Manzano again.
I'm sorry for the delay again.
No, don't worry. So tomorrow we will see.
¿Qué frases son? Estoy preguntando que si es... No,
Sí, ya, ya.